Awesome. Well, thank you everyone for joining the call and the talk. I'm very excited to give this talk. I think a lot of you will find this very interesting, as have I over the last few years. I think it'll be a great supplement for the Chrome Devtools, which you guys already use. Um, so my talk is on going beyond the Chrome Devtools and how the Chrome DevTools get us a good amount of the way for fixing a lot of performance issues. But I think we can go a lot further, and this is what that talk is about. Give me a sec. All right. So a little bit about me. My name is Amila, and before starting Palette, which is the company I'm currently a founder of, I was a performance engineer at Amazon on a team working to cut the load time of Amazon in half. For that, I worked on a number of open source projects from, ESLint related infrastructure to Electron related infrastructure, and a number of other JavaScript infrastructure projects, which you may or may not have used before. But yeah. Now, getting right into it. So, web apps really frustrate users a lot of the time. They're very slow, they're very hard to scale, and and users typically see this because they typically interact with them quite heavily, right? Um, you know, Usually when you're an app, you're usually spending a lot of time in it, interacting with it quite frequently, and this negative experience, a slow experience, compounds over time, and it just reaffirms this negative experience users have. So they get pretty frustrated. Um, so how did we get to this situation where all these web apps that people use every day, like Notion, Slack, Discord, Spotify, they're pretty slow. Like, why is the web in the situation that it is in currently? Well, I decided to like look at, the past year, kind of look at the almost like archaeological view of this and see like how this kind of problem progressed to where it is today. So let's go back all the way to the beginning of the web, like 1994, when we actually had pretty highly interactive web apps. This is 1994, and this is a game of chess, which can be pretty interactive in its own right, right? You have the ability to drag, interact, render, different kinds of input, and it's pretty interactive. And you can see what that Java application applet looked like. You can actually add, event listeners, you can render to the canvas, and you had pretty sophisticated capabilities here. You had multi-threading primitives, which are offered by Java, 3D canvas rendering. It's a statically compiled language, Java, so it's very fast. It didn't have direct DOM access, which was a limitation, but it had very sophisticated features for building these large advanced web apps. Now, chess is one thing, right? But if we keep going, you had Slack, right? So like this is essentially Slack and this IRC. You had very highly interactive applications. This is a financial application with advanced ticker rendering, very very interactive, and even Google Earth, right around that time, the mid '90s, which is like very very impressive, right? So what happened? We had this like fast language for running these large apps in the browser. What happened and why is the web in the state it is in today? Well, in 1995, JavaScript was announced as a sidekick language to Java. It was meant to add lightweight interactivity to web pages. It wasn't meant to be the main language. People were going to be, building these applications in. It was meant for more like, you have a form, you want to add some lightweight interactivity when someone clicks the submit button, something like that. Um, and and then we started building apps on JavaScript, actually entirely on it. One of the first being Google Docs, was called Writely back then. And if you look at it, that's what it looked like back then. Imagine Google Docs today and what it is, what it was back then. But you had all the live interactivity that you do in web apps, text editing, a rich, highly interactive experience, powered by two things mostly: Ajax, XML, HTTP, JavaScript, and then you had JavaScript for live interactivity and rendering and manipulating the DOM in real time to show updates. Um, this was one of the first true web applications built entirely in web native technologies. No Java, no applets, nothing like that. And this really showed people you can have these great experiences in the browser just with JavaScript and Ajax or XHR. So what happened and why are these web apps written in JavaScript so bad and hard to scale, even though they were possible in like 2005 with Google Docs or Writely? Well, when you look at JavaScript as a language compared to Java, it's single-threaded, and that is a main source of contention for a lot of problems in, these web apps. The execution speed is bound to the single core performance of the machine that you're running on. And if you look at single core performance over time, we are actually seeing a plateau over time. We're almost like a kind of like weaving off of Moore's law, in a sense, when it comes to single-threaded performance. If you look at total core performance across multi-threading and the entire performance of the core and the total transistors over the entire CPU, that's actually obeying Moore's law. But the single-threaded performance is actually tapering off, which is a problem for the JavaScript community compared to other communities. JavaScript is also a highly dynamic language. It's very hard to optimize it compared to a static language like Java, which was designed for much more like heavyweight use cases. And also, if you look at the options for where you want to take JavaScript, maybe you want to rewrite in WASM. WASM is a good option, but it's not you can't rewrite everything in WASM. A lot of things that touch the DOM very frequently. There's some overhead for crossing between the barrier from WASM to JavaScript to the DOM. There's a lot of overhead, when it comes to crossing that barrier. So there's some challenges with rewrites as well. Also in web apps, you have many different user flows compared to just, like static sites, right? Like you have, use many different user interactions that can be slow, like typing, clicking. Instead of just load time, you have a number of other kind of interactions that you have to pay attention to. In addition to all of those things, all of the work that you do as a front-end developer has to run under 16 milliseconds for you to hit a 60 frame per second frame rate, which is very, very challenging. You're competing with garbage collection, you're competing with paint, layout, composite, all the other browser, rendering pipeline steps, are what you're competing with essentially. And on top of that, a lot of the code bases for these web apps are more than 1 million lines of code, right? So we have a lot of challenges when building these web apps. We also have very limited observability into what's actually slow for end users. So front-end developers are really facing all of these challenges all at the same time. And this is what makes building web apps incredibly hard today. So let's take a look at how the Chrome Devtools helps here. And the Chrome Devtools is sort of like our bread and butter for looking at a lot of performance issues and fixing them. So let's kind of like start there and see how we like kind of look at it today. So when you look at the Chrome Devtools today, your typical flow for fixing these issues that users complain about is you see a regression, or you get a customer complaint about performance, and then you attempt to reproduce that exact issue in the Chrome DevTools itself, on your own local machine, and you kind of go from there. But the problem with that is that a lot of time reproducing these exact issues the exact same way the user experienced them is actually pretty hard. And especially when your application is very large, you have many different user flows or user states the user could end up in. This tends to be pretty hard to do. It's also error prone, like, maybe it's unit slightly different state. It's a little bit faster phenomena, right? There's also variance in hardware and variance in page state, right? You may not be in the exact same state. And so reproducing performance issues is actually pretty hard and unreliable. A lot of the times you wait for the user to, either submit a video recording or something like that, or even try to record a Chrome trace on their own and send that to you. But these tend to be error prone and pretty problematic and kind of brittle if you're really relying on them. So relying on the Chrome DevTools for these very intricate web app flows and reproducing them takes a lot of time to reproduce, and a lot of times they're not very reliable. So I was thinking of this question. What if the Chrome DevTools was powered by profiling data from end user sessions? If we're able to accomplish this, this fixes a lot of the performance issues and issues with the Chrome DevTools when it comes to reproducing performance issues. So if we had Chrome DevTools powered by the profiling data from end users, this could fix a lot of issues. Users don't have to, rely on manual user reporting. Uh, you can also identify optimization opportunities in aggregate. You have a lot of power by collecting these profiles from end users. Of course, there's some overhead hit, but you get a lot of benefits from that. So, what kind of questions could we answer if we had this gold mine of profiling data from end users? We can answer questions like which functions are impacting the higher percentile metrics of, typing, for example, or which functions have regressed this metric, typing latency, or comparing function performance from like a mid P50 to like a higher percentile of a metric. You can do some pretty interesting stuff here, and this is actually possible today with this API called a self-profiling API. It's been stable for a while now. It's been stable in Chrome since September 2021. And it's a pretty simple API. What it takes is a configuration object, which takes two properties. The first is the sampling interval. So the sampling rate that the profiler runs at, you can see it runs in this interval here by taking snapshots of the stack. That's what that configures. And then you take a sampling buffer size. This is the size of the buffer that these samples are added to. So you can configure your memory overhead there. So this is for CPU overhead. You can configure that. You can configure your memory overhead as well. And to stop the profiler, or this is analogous to hitting the stop recording button in the Chrome Devtools profiler. You just call this API. So this is almost like a programmatic way of interacting with the Chrome Devtools profiler. It's actually very one-to-one in that regard. There's many use cases for it. You can profile third-party scripts, on page load especially. You can profile interactions, which tend to be pretty JavaScript heavy, depending on the application. Page load, React renders, and pretty much any expensive JavaScript part of the application you can profile. It's used by a number of companies, Slack, Microsoft, Facebook, Dropbox, Notion, and many, many more. Yeah, let's dive into how it actually works under the hood. So it's pretty simple when it works under the hood. This is the exact same way it works in the Chrome DevTools. By the way, it's very, 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 very simple. It's actually the exact same API under the hood. It works by sampling the stack at given intervals. It pauses the execution of JavaScript very, very momentarily, takes a snapshot of the stack, and then adds it to this queue, this buffer, and gives you access to that buffer later. So it's pretty straightforward. Say like, so it doesn't work by, as you may think, by starting the trace or the sample at the start of the function and then stopping it at the end of the function and then starting here and then stopping here. It actually takes snapshots at its own interval, which gives you nice performance characteristics and trade-offs. It lets you set the sampling interval, which if you want to lower the overhead of this, you can just run it every, say, like 20 milliseconds rather than 10, which it's doing here. So it gives you programmatic access over the overhead of the API. Speaking of overhead, there is some overhead to using this API, but it is surprisingly low given how it works. So Facebook, one of the largest companies to use this API at scale, has enabled profiling on a subset of their users and has monitored the impact on the load time to be less than 1% with a p-value of 0.05, which is it's very statistically strong. And the reason why the overhead is so low is because this API hooks directly into V8's own internal profiler API and this allows for native and fast, efficient profiling. So it's not like some JavaScript is actually doing all this pausing and whatnot. It's actually happening at the JavaScript engine level. So it's very, very efficient. So this is something to keep in mind. So Palette, which is a company that I'm a founder of, uses this JavaScript API and has built a monitoring service around it. And Notion, which is one of our biggest customers, has also enabled profiling, JavaScript self-profiling API in production to see how it works and to get some more performance characteristics. And here's what they learned just from using this API in production. So from the insights that this API has yielded for them, they've been able to reduce typing latency by 15% across 100 million users, reduce page load latency across 20 to 25%, and identify regressions to page load and typing. And it's enabled the sampler API self-profiling API is enabled on 3% of all the major interactions. And in addition to that, there was no noticeable impact on performance, yielding again to the very low overhead from the via internal integration. So here's the first main use case that Notion has with this API that I think you'd find really interesting. They use it to fix typing regressions. So how does all of these profiles that you collect from end users help with regressions? What's the connection there? So in Palette and a lot of other tools that build on this API, they have the ability to take all of these profiles that you've collected from end users, essentially merge them together and extract some insights from that like merge aggregate profile. And here is what that would look like in one of these kinds of services that you would use. In this case, this is Palette. So in Palette, you have the ability to compare these aggregated merged profiles and see differences in function execution. This is a very standard feature in tools like Datadog and whatnot that let you do this kind of profiling analysis. So in Palette, we have this as well, and then you can see differences in code execution between different versions of your application, for example. So you know so because we collect all these, profiles in aggregate, when we have enough sampling data, you can actually see which functions are taking more time than others. So imagine you were to go into the Chrome Devtools and see a code diff almost of, which functions are taking a little bit more time than others. When comparing across different versions of your application running in production across real end users. This is an incredibly powerful feature, and it really is just a natural extension of what you can do in the Chrome DevTools. It's now just powered by end user data, and it allows you to do this merge, aggregate merge comparison. So it's very, very similar. Um, the great thing about looking at production data is you can see how higher percentiles of your metric are doing. So for example, for the users that have the slowest typing performance, what does code execution look like for them when compared to maybe say like, the rest of the users? So in this case, we're looking at function execution, this code diff, this almost like this like git diff, but for code execution. Um, Increases in execution time, by the way, are shown as red, and decreases in function execution time are shown in green. So this increase in execution time for this specific stack here was a little bit higher for the higher percentile of a metric. We're actually looking at the P80, using this filter of code execution for across all the users in Notion. So this is the kind of data that you can really extract from aggregating these profiles from end users. You get to see what code execution looks like for the slowest users. And a lot of the time, that's actually where your performance issues are. That's actually a lot of time where you actually want to improve performance. It's usually a lot of time those tend to be your heaviest users, with say the largest documents or in Slack with the most amount of channels or something like that, right? So we get some pretty helpful information here on which code got slower. And in this specific case, for Notion, this stack got slower containing the deterministic ID function. And so they knew exactly which code to revert, and their regression immediately was fixed. In Palette, you can see code diffs, and this was the code diff that was added that actually caused a regression to that specific stack. They also fix page load regressions in addition to typing regressions as well. The self-profiling API can be started whenever you want, and you can stop it whenever you want. So you can, profile everything from typing to page loads. And using this API, they were able to fix a 10% regression to the P50, so the median of initial page render. This is one of their page load metrics. And this is what that would look like. So, if as you would expect, there's a lot of Webpack requires here, some very deep stacks for requires. And when looking at this comparison profile, they were able to see that there's this one stack here that was actually unexpectedly added that could have been deferred. but was actually added and was blocking this page load early in the application lifecycle. So by deferring that code path, the code execution of that specific code path, they were able to fix that page load regression. Imagine having to do this in the Chrome DevTools. You don't exactly have the code diffing behavior. You don't exactly see what's getting slower for the P50. So you have a lot less information, a lot less data that you're working with, and a lot of time you can find issues that don't just show up in the Chrome DevTools. The second major use case with the self-profiling API is the ability to find areas to actually optimize performance that aren't showing up in the Chrome DevTools itself. I'll give you a few examples of how Notion does this. So by looking at profiles from end users, you can actually see what code was actually running for a specific user. Previously, where we were looking at aggregates, so code paths merged across all users, but you also have the capability to look at a specific user's session and see what code was executing for them. And this is pretty helpful for looking at areas for optimizing performance. So in looking at this user's session in particular, you can see this one function here, offset, parse offset. And keep in mind that we're looking at the self time here, a inverted call stack. And this one dependency here, the Luxon dependency, was actually taking a surprising amount of time. And during this long task here, this blockage of the main thread for more than I think this looks at almost like 14 seconds it's being blocked for. So you can see some very interesting behavior from end users just by using the self-profiling API. Keep in mind that we are looking at an end user session here, so you can see code execution for a specific user, which gives you different kinds of insights into performance. So by optimizing that specific dependency, the team was able to fix a performance issue with that dependency, and they no longer saw performance issues with that particular use case. This is what that session looks like in a little bit more detail. You can see that parse offset function firing multiple times. Again, this is exactly like what you would see in the Chrome DevTools. And this is the power that you now have. You no longer have to ask a user, hey, like send me the Chrome trace or record a recording of your page or whatever user flow you were having before. Now you can just zoom into it from your observability tool and just see exactly which code was running for yourself without having to ask them. The third major use case is the ability to prevent regressions, which is pretty interesting. So because we have this code diffing kind of performance like git diffing kind of behavior for seeing which functions got slower and faster, you can actually run this kind of tool in an A/B test. You can run Palette or whatever your tool is in an A/B test and test code to see if it got slow or not in the A/B test control compared to the treatment. So in this case, this is just an example here, but the code in red here got slower in the treatment compared to the control here. So those are the major use cases for the self-profiling API. In conclusion, it gives you the ability to fix performance regressions very quickly without having to ask for manual reproductions of performance issues or having to dive into the Chrome DevTools yourself and try to guess at what it is by guessing the user's application state or what have you. It gives you the ability to optimize performance and look for performance opportunities by looking at aggregates or looking at individual user sessions. And it also gives you the opportunity to prevent performance regressions in the form of A/B test enablement. This is a very stable API, the self-profiling API. It was available since September of 2021. It has a less than 1% overhead impact on the load time of your page through native efficient profiling in the V8 profiler itself. And it's used by a number of companies already, just very internally and in production. It's a little bit of it's the best kept secret, I would say, of these companies and their web infra stack. So if you're interested in using this API, We built a platform on this API. All the screenshots that you saw before were from Palette itself. So if you're interested in, using this API and trying it out, you can check out Palette. You can scan the QR code here if you want, if you're interested. And yeah, that's it. Awesome. Let me know if you have any questions. Thank you.